Good day. This is Bennett, also known as Jeremiah. Today I'm going to give you the full understanding of electric circuit. I'm also going to deal with the situations where a lot of students lose marks and they don't know why. I'm also going to deal with the reasoning types of questions. For the playlist, check the top right of the screen. Alright, let's begin. Alright, here is a certain circuit with certain resistors and voltmeters, and the battery is an EMF of 24 volts. Now, in order to understand electricity, I want you to think of current as though they are particles. So think of current as particles. These particles will move around the circuit, so they'll move around the circuit until they finally go back to the battery, and then the process repeats. So now, these particles, for them to move around the circuit, they actually need energy. The energy is supplied by the battery, right? So now, the battery will supply these particles 24 volts. Now EMF is the total voltage supplied by the battery. So the battery will supply 24 volts to these particles, and then these particles will move around. So now when they get here, 4 volts will be taken, and then when they get here, 8 volts will be taken, and then when they get here, 10 volts will be taken. Then by the time they reach the battery, they've got no energy. I want you to notice that the battery on itself has got internal resistance. This is because it has got wires which have got resistance. So inside the battery there is resistance, meaning that energy has to be used inside the battery as well. So these particles which are current need energy not only to pass outside the battery but also to pass through the battery. Alright, I want you to notice that the battery on its own has got internal resistance. This is because it has got wires that have got resistance on its own. This means that the particles which are current need energy to pass inside the battery as well. So the battery caters not only for the external circuit but also for the internal circuit. This is why the EMF of the battery is equals to V external plus V internal. So let me explain exactly what is happening when it comes to this current. So inside the battery there is internal resistance. Let's say the internal resistance is 1, right? So 1 ohm. So the internal resistance, let's just do this. Let me just write it a bit better. So let's say the internal resistance is 1 ohm, right? So we have the internal resistance of 1 ohm. So now let's say the current is 2 amps. So I equals to 2 amps. So now what I want you to notice is that the volts that is required inside the battery, V is equal to I times R. So it means it's just going to be 2 times 1, which is 2, right? So this means that 2 volts will be spent inside the battery. So what actually happens is that, let's say we've got particles, current, right, inside the battery. So the battery will supply 24 volts to the current, but 2 of them will be spent inside the battery. So by the time it comes out of the battery, it will have 22 volts. So notice that the voltage supplied by the battery could have been spent on the external circuit, but some of it has already been used, right? So some of it has already been used inside the battery. So this is why the internal voltage is also known as V lost. So some of it will be used inside the battery. So when it comes out of the battery, it's 22 volts instead of 24. Some of it has been spent in the battery. So it's going to pass on the external circuit, right? So no energy will be taken. But when it gets to the first resistance, 4 volts will be used. So notice that before it was 22 volts, but now it will become 18 volts, right? So when it passes through the resistance, energy will be used. So it's going to move from 22 to 18 because 4 volts has been used. Now when it gets to the next resistance, here it's still 18, but when it passes through this resistance, it's now going to be 10 volts. And then no energy will be taken from here onwards, but when it gets here, it has 10 volts, but 10 of it is going to be used. So when it passes through this resistance, it now has 0 volts. Then it goes back to the battery empty. So every time current returns to the battery, it has got no energy, then the battery resupplies it energy. Then the process repeats. So why am I using this? Why am I explaining this to you? So I want you to notice something. It's very helpful for the questions. So notice potential difference. I want you to notice something about potential difference. Let's just do this. So notice that this measures 4. Whenever it's 4 volts, it's telling you that the difference between the energies before and after is 4, because it will just say it will just say this minus this, right? It will just minus them, and notice that the difference is 4. So we've got 4 volts. So that's voltage potential difference, right? And notice that here also, here it measures 8 volts because it was 18, then it became 10. So the difference is 8 volts. And then here it says 10V because it was 10 and then became 0, so the difference is 10 volts. So it measures the difference. I'll show you what is the importance of this. So voltmeter measures the potential difference. It measures the difference in energy before and after. And always remember, when it comes across a resistance, that's when energy is taken. So why is this important? Now, they can ask you a question. They can say they connect a voltmeter here. And they'll say, write down the reading on V1. Let's call this V1. You have to understand that if there is no resistance, nothing will be used. So if here is 22 volts, here it's also going to be 22 volts. So when you subtract them, it gives you 0. So that is the significance of this. So when it's connected across a path where there is no resistance, V will just be equals to 0. So hence, they just tell you to write down. So let's talk about another type of question that can come out. So let's just do this. Let's call this an open switch. So let's do this. Okay, so now if we have got an open switch, I want you to notice something. Whenever this thing is connected across an open switch, it reads the EMF, right? So they can say the switch is open, then they say write down the reading of V1. You'll say it's 24 volts. That's if they tell you the EMF is 24 volts. So it will read the EMF. Sometimes they can just put this as an open switch and then they give you the reading. If it's an open switch and they give you the reading, that is the EMF. So just remember that whenever the switch is open, this, when it's connected across the battery, it will read the EMF, right? So when a voltmeter is connected across the battery, it reads the EMF when the switch is open. But now, if the switch is instead closed, it will read the external circuit. Notice it's measuring the difference between this part and this part. Remember, we said that when it leaves the battery is 22, right? But when it gets back to the battery is 0. Notice that the difference is 22, and that is not the EMF. That is actually the external circuit, right? The external circuit is 22. So now I want you to notice that the external circuit is always less than the EMF, right? It's only in grade 11 that the EMF was the external circuit, but in metric, they tell you that no, there is actually voltage that is spent inside the battery. So the EMF is the combination of the external circuit and the internal circuit. So let's memorize that part. I want you to memorize that when the switch is open, the voltmeter reads the EMF. But when the switch is closed, when current is now passing, the voltmeter will read the external circuit, right? So it just measures the difference between before and after. So whenever the switch is closed, V reads the external circuit. Why does it read the external circuit? Remember the fact that energy is used inside the battery, right? So by the time it comes out of the battery, by the time it reaches this point, it's 22 volts, right? Because 2 volts has been used inside the battery. So it's going to be 22 volts, then it's going to move around and energy is going to be used, right? Then by the time it gets back to this point, it's 0. So notice that it's just going to say 22 minus 0, so it reads 22. So whenever the switch is closed and the voltmeter is connected across the battery, it reads the external circuit. So just memorize it. Just memorize the fact that if the switch is open and it's connected across the battery, it's going to read the EMF. But if the switch is instead closed and it's connected across the battery as well, it's going to read the external circuit this time. So these are three things to memorize, right? Not that whenever it's connected across no resistor, it reads 0, and then whenever it's connected across the battery and the switch is open, it reads the EMF, but whenever it's connected across the battery and the switch is closed, it reads the external voltage of the circuit. So that is it. Now let me deal with something that confuses a lot of students. Here is a particular shape that comes out in many past papers. And unfortunately, a lot of people don't know how to calculate the equivalent resistance. Some students will actually say this is parallel to this and this is parallel to this, and they will get it wrong. Many other mistakes I've seen. So let me give you a skill that will enable you to be able to calculate the equivalent resistance in any situation. Alright, let's deal with an easier situation, then I'll build from here. So if they say calculate the external, or rather the equivalent resistance, it's easy, right? What you will say is that these are parallel to each other, so we'd use the formula 1 over 2 plus 1 over 4, right? That is actually 1 over, just be careful that is 1 over, and it's not RP, it's 1 over RP. So then this will end up giving you, matter of fact, this is supposed to be 4. So then this is going to end up giving you, let's just do this. This is going to end up being 8. Then it's going to be 4 and 2. So this is going to be 6 over 8, right? So now 1 over RP is going to be 6 over 8. So let's just do that. So it's going to be 6 over 8. And then there is a scale. You can actually switch, right? So if I put RP on top and 1 down is RP over 1, which is just the same as RP. And then I can also switch, right? It's another scale in solving for x, 8 over 6, right? So RP is 8 over 6. So what you will do is that you will calculate this portion first, right? Which is 8 over 6, and then you'll add it to the series one, right? So you'll easily say it's going to be 8 over 6 plus 6, right? And then you get your answer, you get your equivalent resistance. Now let's go to level 2. This is the beginning of the portion where people get it wrong, and I'm going to explain it. So when I give you a question, you're going to pause the video and you are going to attempt it, and then you're going to compare. So what if I put another resistance over here? Let's just say put another resistance over here. Let's say the size of it is, let's say 2 as well. So you can pause the video and calculate the equivalent resistance. So a lot of people get it wrong because they don't look at paths. Let's talk about paths. So now notice that current will pass here, right? And then when it gets here, this is where it splits. So for you not to get it wrong, for you to always get it right when it comes to parallel circuits, you need to know where they split and where they join. Notice that it splits here, right? So it splits. So when it splits, it means that this is one path and this is one path, and then they meet here, right? So always consider where they meet and where they rejoin. So notice that we're going to have the splitting point. This is the splitting point, and this is the joining point, right? So how you calculate the equivalent resistance, let's do the parallel circuit first. How you calculate the parallel circuit is that, notice, this is one path. So because it's one path, it means that these two together are in series. So it means that the combination of these two is what is parallel to this one, right? Because this is in its own path. So what you're going to do is that you're going to say this is 2 plus 2, which is 4. So now you're going to say 1 over RP is equals to 1 over 4 plus 1 over 4, right? Because these two are in parallel with this. So these two are in series, so you have to add these two together. So this is going to be 4, right? So the combination of this is what is parallel to this one. So then it's going to become, you take this as 1, right? The combination of this stuff is just 4. So it's going to be 1 over 4, and then it's going to be plus that 1 over 4, since the combination of this is parallel to this one. So let's just go further. So now we're going to have 1 over RP is equals to, it's just going to be 2 over 4, which is 1 over 2. So if you solve, you'll just end up getting RP as, you can even use the method that I just used, right, which you just switch. So if I switch, RP is going to be on top, 1 is going to be down, and then 4 is going to be on top, 2 is going to be down. So there is no need of me saying over 1, so I can just remove it. So RP is 4 over 2, which is 2. So RP is 2, and then I add the answer to this 6, so it becomes 8. That's the equivalent resistance. So let me add one more level, and then we shall go to that shape that confuses a lot of people, and then we shall move forward. Alright, here is another question. So I want you to pause the video and attempt the question. So what I want you to notice is that current passes here, and then we have the splitting point here, right? So when it splits, it means that this whole thing is taken as 1, meaning that these two are in series. This is what you have to add. So 2 plus 2, 4, right? And then also this portion is 1, right? So it means we have to add this. This is 7, right? Because the next joining point is here. So that's how it is. So notice that we have got the splitting point, right? So we've got the splitting point here, and we've got a joining point here, right? So it means that this is one path, right? This is literally one path. And this is one path as well, right? So this is one path. So it means that the combination of this is parallel to the combination of this, literally. So what you have to do is that you have to add this in series first. So 2 plus 2 is 4, and 3 plus 4 is 7. So then for us to get the RP, we're going to say 1 over RP is equals to 1 over 4 plus, right, 1 over the combination of this, right, these two are in series, so we're just going to say 1 over this. So 1 over 4 plus 1 over 7, because the combination of this is what is parallel to the combination of that. So we just say 1 over 4 plus 1 over 7. So then this becomes 1 over RP is equals to, so this is going to end up becoming 28, and then we're going to have 7 and then 4. So it's going to be 1 over RP is equals to 11 over 28. So therefore, it means that if I switch, it's going to become RP, all right? RP over 1. Okay, let's just write it a bit better. So let me just write it a bit better. So it's just going to become RP over 1 is equals to 28 over 11. So RP is just equals to 28 over 11, right? So then I add it to this one that is in series, because the combination of all this stuff is in series with this one, right? So then it's just going to be 28 over 11 plus 6. So the answer of that is the equivalent resistance. So I'm not using a calculator, hence I won't waste time adding it, even though it's easy, it's not hard. All right, so now let's go to another one. So let me show you another situation. Here is the situation again, right? We're given this stuff. So how do we calculate the internal resistance? I want you to pause the video and attempt this one. So notice that current is going to pass here, right? So it's going to split here. This is the first splitting point. So it means that this is literally 1, right? And then this is one part, like this whole thing is one part, because notice that it splits here and it joins here, right? So this is one part, and this whole thing is literally one part. So what you're going to do is that 1, 2, 3, the combination of these 3 are parallel to this, right? So the combination of these 3 is just parallel to that one. So what we're going to do is that we're going to add these 3 in series. So 4 plus 5 is 9, plus 6 is 15. So then it just means that the combination of this gives us 15, right? So the combination of this is what is parallel to this. So we're going to say 1 over RP is equals to 1 over 15 plus 1 over 3. So then this becomes 1 over RP is equals to 45, and then we've got 3, and then we've got 15. So it becomes 1 over RP is equals to 18 over 45. Therefore, RP is just equals to 45. Okay, so just forgive my handwriting there. So I just don't want to spend much time in this. 45 over 18. Right, so that's what we have. So that's what we got for RP. So all of these are in series with that one. So our equivalent resistance will just be 45 over 18 plus 7. So I hope you get it. Notice that these 3, right? Because notice they split here. Current, notice that current will be passing here. So they split here. So when they split, this is one part and this is another part, the whole of this, before they join again. So therefore 1, 2, 3 are in series, and the combination of these 3 are in parallel with that one. So that is it. So that's how we deal with parallel circuits. So if you got this right, yep, you now have the skills to never get it wrong. Literally, the majority get it wrong.
Just before I continue, if you want to be tutored, whether it is online or physically, Whether it is the situation where you're struggling in maths or whether it is the situation where you're good in maths but want perfection, take a screenshot or save these details. Whether you're studying Cambridge, which is the UK curriculum, or whether you're studying NSC, which is the South African curriculum, or IEB, or native courses which start from N1 to N6, or any curriculum you're doing no matter which country you're at, we offer tutorials. We've got lessons and practice sessions 5 days a week. We also give you tests once a week.
Watch the video that is found at the end of this video in order to know the prices and the updated contact details just in case these ones have changed. Alright, let's proceed. Alright, here is the situation. Now they can ask you, what will happen to the external voltage? So what will happen to external voltage if this is deleted? So if this is removed from the circuit, what happens to the external voltage? What you have to know is that you have to use series to remind you. You can use series to remind you. So remember, in series, the more we add, the more the total voltage increases, because for us to get the total voltage, we always add them, right? So the more we add resistance, the more it increases. So the more we remove resistance in series, the more it decreases. But in parallel is the opposite. So you can use series to remind you. So if they ask you what will happen if you remove it, you can think of in series. In series, if I remove, what happens? The total resistance decreases. So therefore, it means in parallel, the total resistance will increase. So you can use series to remind you. Just remember to use the opposite after you've used series. So in series, if I remove, the total resistance will decrease. Therefore, in parallel, if I remove, the total resistance will increase. So with no matter what type of question they ask you, whether it comes to the brightness of the bulb or the total voltage or a certain reading on V, right? You always use this reasoning. You have to check what happens to the total resistance. So here, if I remove the resistance, right, in parallel, the total resistance increases. So you always start by resistance. So you tell them RT increases. After you have told them the total resistance increases, what happens to current? Remember, I is equals to V over R, right? Therefore, current and resistance are inversely proportional, right? So you tell them in words that the total, you tell them in words that if we remove maybe R3, whatever they call it, you tell them in words that if we remove R3, the total resistance will increase. Then after you tell them that, you tell them that therefore current will decrease, because current is inversely proportional to resistance, right? So there's marks for this. So you will always start by the resistance. So here, because resistance increases, current decreases. And then after talking about current, you have to talk about lost volt, right? So remember the formula, EMF is equals to V external plus, okay, let's just do this, V external plus V internal, or V lost, right? So now I want you to notice that V lost, so notice that V lost is equals to I times small r, right? So you tell them that if current decreases, V lost also decreases, because notice if current goes down, V lost also goes down. So always, this is the order. You always tell them that if current increases, rather if resistance increases, current decreases. And if current decreases, V lost will also decrease, right? After you have talked about V lost, notice that here V lost has to go down, right? After you have talked about V lost, EMF is always constant for the battery. So if this goes down, for this to remain constant, this has to become bigger. That's how it is, right? So I want you to understand that EMF always remains constant. So if V lost goes down, V external will have to increase. So that is the procedure. You'll first tell them that the total resistance will increase in this case, right? So you tell them that the total resistance will increase. Then afterwards, you tell them that therefore current will decrease. And since current will decrease, V lost will decrease. And then since V lost will decrease, for the EMF to remain constant, V external will increase, right? So if V external will increase, then that's it. You're telling them that this will increase. You said therefore the reading on V2 or whatever they ask will increase. Same thing as if they ask for the brightness of the light bulb. If they say what will happen if this is deleted, if this is deleted, notice that in series when we delete, resistance decreases. Therefore, in parallel, when we delete, resistance increase, right? So you tell them that if this is deleted, the total resistance will increase. And if the total resistance is increased, current will decrease. And since current is decreased, V loss will decrease. And then since V loss is decreased, external voltage will increase, right? So therefore, this will become brighter. Literally, that's how it is. If they ask about the power, since external voltage increases, power will become more. Literally, that's how it is. So it's that easy. So I have to show you some other type of weird questions. So they can tell you that, by the way, if they tell you about a variable resistor, don't get confused. It just means a resistor that can change size. You can set it to whatever you want. You can set it to 2 ohms, you can set it to 3 ohms and stuff. So let me talk about another question. So in another question, they can tell you that this is now removed and is replaced with an amp meter. So if they replace this with either an amp meter, so literally they can tell you that they just removed this and they replaced it with either an amp meter or a voltmeter. So if they give you either an amp meter or a voltmeter or even an ohm meter itself, right? So as long as it just has meter. So if they replace it with an amp meter or a voltmeter or an ohm meter, they can ask you what will happen. So what will happen to maybe the brightness of the light bulb? You'll tell them that if you remove this and you replace it with an amp meter, the amp meter has very high resistance. So now I want you to understand that the amp meter's resistance, or voltmeter, or even an ohm meter, right? The amp meter's resistance is so high that if you put it in place of the ohm meter, no current will pass through here, literally. So in other words, it's another way of saying I'm deleting this part again. Literally, they're just asking the same question in another way. So if they tell you that they are removing this 3 ohm resistor and they are replacing it with an amp meter, the amp meter has got a high resistance, so much so that current will not pass through here. Remember, current always divides, right? Current always divides, and it always passes more where there is less resistance, right? But now here the resistance is going to be so high that no current will pass here. So it's as though they're deleting this part. So if they tell you that they remove this and they replace it with a very high resistance ohm meter, then you must just interpret it as they are just deleting this part. Then you interpret it the same way. You tell them that since no current will pass here, for marks you tell them that an ammeter has got very high resistance. There's 1 mark for it, and then you tell them that no current will pass through here, right? And then you tell them that the total external resistance will increase. Remember, when you remove resistance in parallel, it increases. So you'll tell them that the total resistance will increase. Then after telling them that the total resistance will increase, then you talk about current, then you talk about V loss, then you talk about V external, then finally you can talk about the brightness of the bulb. So now let's deal with another type of question as well. So they can say this is removed and is replaced with a variable resistor. Now that resistor is set to 0 ohms. So if they put a resistor that is set to 0 ohms, or if they simply delete this resistance but they don't remove the wire, what are they doing? If the ohms is 0, remember, let's just say the ohms is 0. If the ohms is 0, remember, current always divides, but it always passes more where there is less resistance, right? But now if this is 0 ohms, it means that all the current will pass here. Because think of it, it's comparing 0 and 2 ohms. All of them will pass here, literally. So whenever they remove this, but they do not remove the wire, or they just tell you that they put a variable resistor and they set it to 0 ohms, all the current will pass here. So you will tell them that it will be a shortcut, right? You tell them that you are providing a shortcut for current. So all the current will pass here, right? Literally, so all the current will pass here. So it means that there won't be a reading on this, there won't be a brightness, right? There won't be a power here, there won't be a brightness, or there won't be whatever voltage is here, whatever they ask here, right? Because all the current will pass here. So literally, that is how it is. Yeah, so that's how it is. I'm just looking for another thing to explain, but I think that is it. So the only thing that I didn't explain is when we talk about power, right? When we talk about power, you know, these formulas and stuff. So I just have to create a video where we now tackle past papers. But this is it. This is the whole understanding. So I hope you get it. So especially...
Alright, we have reached the end of this video. I have included a playlist of similar type of questions. If you enjoyed this video, please like the video and subscribe to my channel. Any questions you've got or any video you want me to create, Please comment below. See you in the next video.